5 years ago, a NASA-funded science team ventured onto an ever-changing region of the Greenland ice sheet in the peak of summer melt season, when the ice was literally melting out from under their feet. What they learned is changing the way we think about the movement of ice sheets, and possibly changing our computer models that predict how fast ice will melt, a question which matters to every coastline on the planet.
The number one reason we are here is all about global sea level rise. Greenland is the single largest melting chunk of ice in the world. What really matters to the world is how much of that water melted on the ice sheet gets out to the ocean.
In order to collect this data, the team had to first transport scientific equipment and survival gear to Greenland, and then travel via helicopter to set up camp in the ablation zone, a region of melting ice.
Camping out here logistically is very difficult. We're camping in the ablation zone. It's very wet, as you can see. The ablation zone is where it is melting over the summer. Even talking to the logistics coordinators, they're very interested in our camp because they're trying to learn things about how do you camp in the ablation zone.
One lesson is to be quick and nimble. The team had to evacuate from the first spot they scouted because the surface started melting right under their camp. So what big science questions are at the heart of this bold undertaking?
In 2015, when we started this study, there was surprisingly little attention paid to the hydrology of streams and rivers on the ice sheet, especially inland away from the ice edge. And we felt that this was a critical scientific gap. Just from looking at satellite images of the ice sheet, it was very apparent that very large volumes of meltwater were moving through these systems. And one of the things we learned is that the total volume of water passing through these river systems far exceeds the volume of water contained by lakes. Much like the terrestrial land surface, lakes catch your eye because they're so big, but the real action, the real flux is through the rivers.
All of these rivers terminate in a stunning and dangerous feature called a molten, which is essentially a sinkhole in the glacier surface that develops when these large rivers melt down into the ice to a point where they encounter a crack of some type. At that point, the river is captured and it ceases to flow over the surface of the ice sheet and instead plummets down into the interior. And this year, we mapped 538 of these very large blue rivers and showed that every single one of them terminates in one of these moulins. So water that's melted on top of the ice sheet is quickly and effectively gathered and transferred through these branching stream and river network systems. They are swept off the surface of the sheet within a matter of a few hours or even less, and ultimately emerge 80 kilometers from here at the ice edge.
The team used a couple innovative techniques to measure the river. First, working in shifts, they measured stream flow for 72 straight hours using an instrument mounted on a boogie board that uses sonic beams to measure the depth of the water and the speed of the current. To do this, they had to climb out to the very edge of the water.
Basically, the most important here is that we all come back home. The reason why this is a dangerous place is because only a couple of 100, 200 meters downstream of where these guys are working right now is a molten. This is a vertical passageway, a hole where meltwater goes straight into the ice. You see this river behind us. This blue river flowing very fast, very powerful, very cold. If one of us would fall into this river without being secured to something, we would just flow like a little leaf into that big hole, and that's it.
By far the best solution to ever having to deal with someone taking a spill is to make it impossible for them to fall in the first place. So the way we do that is to put them on a leash, where the leash is exactly long enough to get close to the water's edge, but not 1 inch more.
In addition to measuring stream flow with instruments on boogie boards, they also flew several kilometers upstream to 3 different tributaries of the Study River and deployed the last 3 autonomous drifters built by the late scientist and engineering wizard Alberto Bear.
These are GPS autonomous drifters, which will send the GPS coordinates of the location as they flow down a river. What that tells us is its velocity, and that's very helpful because when we set up these cross sections, we're in one point location. With the drifters, we get a longitudinal long profile, and then we lose the signal when they go down into a moulin. And as it gets closer to moulin, so the rivers actually don't get that much deeper, they just get kind of faster, and then they incise into the ice, so these big canyons. So the point of the drifters is to map the hydraulics of the big, fast rivers that we can't get close to.
An hour later, all 3 drifters, which had been placed in 3 separate streams at different times, came floating into view at once, sending a chill of excitement through everyone on the team. After analyzing their hard-won 2015 data, the team was a bit puzzled by one thing. The heat budget calculated by satellite observations, computer models, and the scientists' mobile weather stations predicted that current temperatures should be warm enough to melt more ice and create more runoff than the scientists were actually measuring. So what was missing from the models? The team returned to the field site the following year, this time collecting an entire week of flow data, and also decided to look more closely at the surface of the ice itself.
And when we drilled into it, we found up to 1 meter of soaking, wet, rotten, fragmented ice. You could break it apart with your hands. And it stores a non-trivial amount of water, and it also creates the opportunity for water that is melted during the day to refreeze at night. And when it refreezes at night, it needs to be melted the following day in order to return back into meltwater again.
Melting again the next day requires more energy. This was the energy that the models assumed was only melting ice once, rather than having to do it twice.
And this is great because we're working with modelers and we're going to get that process now into the models, and the models will get even better. And field teams and modelers have been working this way hand in hand since the 1960s, and it's why the models keep getting better and better.
In addition to measuring stream flow and solving the mystery of the missing meltwater, the team learned something about the reflectivity of the ice, known as the ice albedo. Basic physics tells us that the darker something is, the faster it absorbs the sun's heat.
And you can see this when you fly around Greenland and you look at it. When that snow line pulls back, you can see the darker blue ice revealed. And that bare, exposed, darker ice absorbs more sunlight than it would if it was snow covered.
And likewise, other things covering the ice, like algae or dust or soot from engines and factories or volcanic ash, can also have a darkening effect. But their study showed that the snow line itself was 5 times more important to melt rates than these other processes.
One factor that's a little worrisome is that owing to the topographic profile of the ice sheet, it gets flatter as you go to higher elevation. What that means is as the snowline elevation goes higher under a warming climate, the area of ice exposed will increase as we approach the flatter parts of the ice sheet.
Finally, the team observed that when surges of water enter a moulin in a particular location, it's often followed within a couple hours by a surge of ice movement above. That meltwater can act like a layer of lubrication and allow regions of the ice sheet to slide more rapidly. Increased ice motion can result in an increase in iceberg calving and other positive feedbacks which affect sea level rise. A new study, including members of the team and NASA Goddard glaciologist Lauren Andrews, concluded that the most important factor influencing daily changes in glacier speed in southwest Greenland was not necessarily the volume of the water, but how quickly the volume of water entering the subglacial system changes. The faster water enters the subglacial system, the higher the subglacial water pressure, essentially creating an effect like when the tread of tires on a car are overwhelmed by water on a wet road, causing the car to hydroplane. The intimate workings of the Greenland ice sheet may seem like a distant concern to those of us thousands of miles away, but their effects will be widespread.
The sea level rise presents an existential threat to core cities and populations all around the world. A majority of our major cities are on coastal deltas, so it's very important. And our ice sheets are the biggest contributor to that. And Greenland is one of them, but of course, Antarctica, the stability of the West Antarctic ice sheet is the other elephant in the room. I think that 5 years from now, our sea level rise projection models from Greenland, which are already excellent, will be even better and more dependable. We know quite a lot now, but not enough.